Okay, welcome at Janson at FOSDEM 2024. Firefox Power Profiling. We'll listen to Florian Quèze. Welcome.
Hello, I'm Florian Quèze. I'm a performance engineer at Mozilla. For the last few years, I worked on understanding how much power is used by Firefox and how it's used, how we could reduce it. And today, I will be sharing how the tooling we've put in place to understand Firefox power use can be used to improve web sustainability. So first, I will explain what I mean with web sustainability. I mostly talk about carbon footprint when I'm thinking sustainability here. And there are three main components of the carbon footprint of browsing the web. The first and biggest one is the user device. Then the second component is whatever's not in front of the user. So that includes networking, server equipment. And then the power used on the device by the browser when browsing to see the web page the user wants to see. So let's look at each of the three. First, the user device. Usually we think it's not within our control when we develop a website, because it's the user who picks the device. We have nothing to do there. The emission we are talking about here, it's the embodied emission. It's the emission whenever someone is buying a new computer or a new smartphone. So it's the emissions to produce this device, to manufacture it, but also to ship it to the user. And even though we don't get to do anything about the actual emissions when creating the device, we can reduce the incentive for the user to replace the device. And the ways we can do that is to ensure good performance, because something feeling too slow is a strong incentive for someone to replace a device. And the other thing is ensuring web compatibility. Because if a device becomes incompatible, the user has to replace it or update it in some way. And on this topic, I would like to mention that Firefox is currently the only browser that is left supporting Windows 7 users. And we actually still have millions of users running Windows 7. So if you are thinking about sustainability, web compat is one of the first things, and think about Firefox CSR. Second piece of carbon footprint is the emissions for the infrastructure, anything server, networking. I'm not going to talk a lot about this because it's already well covered, and there's a reason for that. It's that the financial cost of operating the services scales mostly with the emissions. So there are strong incentives to optimize, and there's already a lot of tooling available. And last, and maybe not least, very often neglected, the emission caused by using the browser to display the web page. And the reason why it's neglected is that in people's mind, there's no good tooling available to look at those. Is that correct? Well, not really anymore, and this is what I will be talking about today. It's what we've done to change this. Will be the focus for today. So, because the talk is 40 minutes long, I want to give you the structure. First, I will explain why, as Mozilla, we care about this. Then I will explain our journey to measure power use locally, what we've done to be able to understand it. And then I will go deep into the topic of power profiling. But first, I will introduce the Firefox profiler so that even if you don't know it yet, you can make sense of it. Then I will explain what power profiling does and show examples. Examples are important because this is where we see why all of this makes sense. And then we will take a break from the structured presentation of slides. I will try to do a live demo if I have enough internet. And then I will explain what we call external power profiling, whatever that is, and give some more examples. So let's start. Why do we care about this as Mozilla? There are three main reasons. The first one is for sustainability. Mozilla made climate commitments of being carbon neutral, of reducing our footprint year over year, of leading openly by sharing materials, tools, and methodologies. That's what I'm doing today. And of improving products from a sustainability perspective. There's a reason why this one matters. It's on the next slide. It's when we look at Mozilla's carbon footprint, the actual footprint caused by using our products on our users' devices is more than 90%. And by the way, when we say we are leading on sustainability, we are the only browser maker organization that actually publishes this kind of data. The others, they are shy about it. And we would like to encourage others to also publish this kind of data. Second reason for caring about power use of Firefox, and a very important one, it's for user experience. Nobody likes to use a computer that uses too much power, and there are multiple reasons. One, it's causing noise with the fans. If it's a laptop and it's super hot, it's painful. And then even the people who couldn't care less about climate change because they think it's somebody else's problem, they hate running out of battery. So battery life matters to everybody. And then last but not least, we do this for a better web. And there's a reason why we want to do this. It's Mozilla's mission. We are building a better internet. This is what we are here for. And because Firefox is made on web technologies, everything we do to make Firefox more energy efficient and all the tooling we put in place, it's directly reusable for our web pages. Now let's dig into our journey to figure out local power use. I started a couple years ago. My task was to figure out how Firefox uses power, what should we do about it. It was not clearer than that, it's just let's look into it. So when you want to understand the power use of something, the first thing you do is you take an energy meter, a watt meter. So that's what I did. It's cheap, it's easy, it's pretty accurate in terms of the data it shows. It's also pretty useless for the case of software, because software is not something that you start and it does the same thing all the time. You need to see evolution over time, and I was not seeing anything. So next step is get a better watt meter. I got some that is communicating to the computer through Bluetooth. It's sending me something like this, so I can see a chart. It's much better. It's still not so great because I still can't correlate with what we were doing with the code in the browser. And at that point, I wondered, how is the competition doing it? And I found this blog post from Microsoft that I found very interesting. It's back when they were working super hard on Edge battery life. They were super proud of it. It was before they switched to Chromium. And one sentence really caught my attention. That's the one highlighted in blue here. Power was measured on the Surface Book because it has integrated hardware instrumentation. So that's how Microsoft did it. They have their own brands of laptops. They put built-in power meter chips in those so that they could compare power use of Edge with competing browsers. So that's not really something we can do as Mozilla. We don't make laptops. But can I get some of those Microsoft laptops? Well, sure. So I actually found two that include those power meters. They are pretty old because they are back from when Microsoft was doing this kind of work. They still work. I tried to find newer devices, but unfortunately, all the devices where I found that a device like a power meter is exposed in the ACPI table actually doesn't seem to be actually present on the device. So I think those power meters were put in by manufacturers for prototyping and calibrating battery discharge rates, and then not put into production devices. And when we look at the tool called Perfmon on Windows, on those computers, we get something like this. We see energy meters, and we have 4 channels here, battery, CPU, GPU, and the Wi-Fi chip, which means we can measure the power use of each of those components. We can measure it, we see something like this. So we now have charts, we can try to correlate with stuff that happened. I'm not sure if you think like me, but I really dislike this UI. I find it absolutely terrible. I can't make sense of it. Even the unit I can't make sense. Like here I selected the CPU core's energy, and it's using, last time it was measured, 5 point something E plus 0.11. Whatever that means. While searching for those devices with built-in power meters, I had a good surprise. On some laptops, the names of energy meters were pretty familiar if you use Intel Power Gadget. Those are the RAPL channels that are exposed by the CPU itself. After some investigation, it turns out that all Windows computers with Intel CPUs expose the actual CPU as a built-in power meter, and we can access it. Because, another nice surprise, there's a documented API for it. I have not found any example of someone using the API, but the API is documented, which means I can now understand what the unit was. So the E plus 11, it was because it was picowatt hours. And we can query it many times per second, so I know that because I experimented with it. Very little overhead, so I can query it many times. And the most important thing for us is it's accessible in user land. I absolutely don't want anybody to run Firefox as root to be able to power profile it. So accessing as user land without requiring users to install anything was very, very important for us. So all of this makes it pretty tempting to use for profiler counters. And at this point, I started prototyping something, started hacking. And this is the screenshot of the very first power profiling prototype I got of Firefox. So we see the same name here, RAPL channels. So it's not very user-friendly as names here. And the units were not correct, but the thing that matters a lot when seeing this screenshot is the shape here of the track. So this is the CPU package, and you can see that it matches the shape of when we were using CPU. So the data seems correct. We were using CPU here too, and there's a shape that's moving here. PP1 is the GPU, and there's a spike whenever we do something on screen. We were doing graphics work here, and we had something here, something here, something here. So the shape is correct, and this is a key validation because until then we were thinking we could not power profile, because power profiling means running the profiler. Running the profiler means using power, and we were afraid we would be profiling the profiler, which is not what we want. And this validates that it actually worked. So I decided to polish it and make it something we could ship. But I shared with you a screenshot of a profiler without introducing the profiler. So now is a good time to introduce it. What's the profiler? It's built into Firefox. No additional tooling required. It's always there. The user interface is not there because we don't want to clutter things for all users. But it's trivial to make it show up. And it was created for performance work. And here by performance, I mean making things faster. It's useful both for users so that they can make useful bug reports very quickly. Instead of saying something is slow, they can say, here's a profile of what happened, please have a look. And useful for developers because those profiles are easily actionable. And it's one of the best profilers that exists currently, and there's a good reason for that. We started investing heavily in it in the Firefox Quantum days. On those days when we decided that the engineering teams of Firefox being several times smaller than all of the competitor teams was definitely not a good reason for Firefox to be slower. So we needed better tooling. Profiler uses multiple sources of data. It's a sampling profiler, which means that it uses a timer, and at a fixed interval it stops the execution of the program, and will capture information. Typically it will capture stacks of all the threads we care about, and it will also capture counter values. So counters, for example, if we care about memory use, whenever memory is allocated or released, we will increment or decrement a counter, and then when sampling, we record the value of that counter at the time we sampled. And the last source of information is markers. Markers can be seen as annotations left by the developers so that whenever we see a profile, we see what happened at the time. I had screenshots of showing how to use the profiler, but I will try to do a demo instead. It will be more interactive. So this is a Firefox Nightly instance that is created fresh, no user profile. And I will go to profiler.firefox.com. It loads this web page. And I will click the big Enable Firefox Profiler menu button. When I click this, I see a new toolbar icon that appears in my toolbar. It was already there, just we are showing the icon when clicking that button. And I have settings here. In most cases, the default settings will be good for what you want to do. So you can just click Start Recording, and then you can start doing what you want to profile. So I will, for example, load the Wikipedia homepage. And once I'm done doing the thing I want to profile, I can click the button in the toolbar again. A second or so later, I have a new tab that opens, which is my profile. The UI might be a bit intimidating at first. I will go through it with you. There are two main pieces of the UI. The first one is the top half here, which is what we call the timeline because everything is drawn against time. There's a time ruler here. And then there are panels at the bottom. So in the timeline, you can see that we have what we call tracks here. And there are tracks for processes, like you see the parent process here. In Firefox, the parent process handles the user interface and the rendering. And you can see a process for each content process. So for example, I have a Wikipedia process here that I will select. And here there's activity, so I can make a selection, and I can zoom into it by clicking this magnifier icon. So now we'll see in a lot more detail what happened. And the UI is very interactive. Whenever I move the mouse somewhere, I will see a tooltip showing me what happened. So here I'm seeing the stacks that were sampled. I see there's some JavaScript in here. I assume some of you are web developers and probably care more about what JavaScript runs, so we can filter frames to JavaScript only. And here I'm seeing which JavaScript code was run by Wikipedia when loading the page. I also said we have markers, so I will show an example. In the panels at the bottom, I have a marker chart. And if I go here, I have DOM events. They show whatever events were sent to the web page. And if I scroll down, I have many more. I won't go through all of them, of course, because we clearly don't have time. I just wanted to show the awake markers here that show whenever the thread was active, which is important for power use. And the runnable markers we have at the bottom here that show the name of the C++ task that was running, which is very important for Gecko developers when you send them one of the profiles. So that will be it for an introduction of the profiler itself. I will go back to the presentation and skip all the screenshots I had that show the same thing. And now we'll talk about actual power profiling. So I said we had a working prototype, now we want to make it work for real. So it's built in, again, no extra tooling required. It supports the 3 major desktop platforms. We shipped it in Firefox 104, so that's already a little while ago. We got a lot of great feedback on it, especially from people who care about sustainability of the web. To the best of my knowledge, it's not been copied yet, but that might happen at some point. Platform support. On Windows 10, we support only the devices that include built-in power meters. On Windows 11, with Intel CPUs, we have information about CPU, integrated GPU, and memory power use. And on Windows 11 22H2, that update, we started seeing Windows supporting AMD Ryzen CPUs, and a good surprise here is there separate information for each core, which means that if we can track which process was using which core for which thread, we can know exactly how much power is used by the code we are running. On Mac, we support both Apple Silicon CPUs and Intel CPUs, different ways. For Apple Silicon, we actually have an API from the kernel that gives us information about the amount of energy used by each process, and I think Apple can do it because they control both the CPU chip and the kernel. It's very likely that whenever they context switch a thread, they record the value of the counter, and that's how we get the value. And for Intel, there's a very obscure system call that can be called only from assembly, otherwise we crash, that gives us the value of the RAPL model-specific registers. I'm very happy I didn't have to figure this out on my own. A former colleague did it several years ago. I could just copy-paste the code. That was nice. Last but not least, Linux. On Linux, we use RAPL perf events. Those used to be unrestricted, but then there was a side channel attack. And the reason for that is if you look on Windows, you can access the power data up to once per millisecond. If you try to access it faster, you will get the same data returned again. On Linux, there's no rate limit like this, which means that you could query it so often that you could guess some information about the data being processed. So when this was discovered, it was then restricted to only be accessed by root. Thankfully, there's a command we can run as root that lets the kernel know that it's fine to not be paranoid about it. And that's the exact same command that needs to be run to use Linux perf, the built-in profiler for Linux. So I think it's fine. As long as users don't need to run Firefox as root, I'm still happy. So I will take this workaround. AMD CPUs are supported. A word of warning, it doesn't work on snap packages if you're on Ubuntu. The binaries provided by Mozilla work. And I think that's because the packaging system puts some restriction on what's allowed or not. A few words about how to configure a profiler. I said in my previous demo that the default settings are right in most cases. If you want to power profile, they are not right. Because obviously you want to also include the power use feature that's down here, the checkbox you see there, and also markers for all threads. And the reason for that is waking up a thread has a cost in terms of power, and we want to know about it even if it happens on threads we were not profiling. So we want to know wherever it happens. And I selected the power preset, of course. And the other thing we want to do is reduce the overhead. As I said, we were concerned we might be power profiling the profiler itself, which is useless. So what we are doing is increasing the sampling interval. Instead of sampling every millisecond, we sample every 10, reducing significantly the overhead of waking up. And when sampling, we don't capture the stacks. We only capture counter values. We still have all the markers that still give plenty of information. Throughout the presentation, I will give plenty of examples. And as I said, the profiler UI is very interactive. So here's a link to my slides. And whenever I have a screenshot of a profile, I also have a link to the profile so that you can see the profile for yourself. One thing I should mention is that the share.firefox.dev domain doesn't work with IPv6, so you need to be on the FOSDEM dual stack Wi-Fi network if you want to be able to click right now. First example of power profiling. I will go through it with you because I know the profiler UI is intimidating. It's the same thing as what I was doing before, which is loading the Wikipedia homepage. And we can see on the screenshot near the top. It was not visible. So the screenshot here, we see it was not loaded yet, but there was CPU activity. Here something starts appearing, and here it's visually complete. So I made a selection here of the part of the profile that we care about. You see we have the parent process. We no longer have colors, and we no longer have stack samples because it's the power profiling settings. We still see the network requests. They're also shown here. And we have a new process power track here that gives us how much power is used by the parent process. We have a similar track here for the content process that tells us how much power was used at any given time and the amount of energy used. So here, 134 microwatt hours. So that's how much power it takes to load Wikipedia, apparently, on that computer. Second example, this is profiling on Windows 11, and this is starting Firefox. And you can see how much, so this is the CPU activity when starting Firefox. You can see that here we had a window, and here it was visually complete. And the activity was done. So we can see how much power was used by the CPU cores, the built-in GPU, and the entire CPU package. And here it's selected, and we see it used 10 milliwatt hours to start Firefox on that specific Windows laptop. I'm not sure about you, but for me, whenever I have new tools, I like to play with them, and I like to test their limits. And I was wondering what's the tiniest thing I could power profile reliably. And this is the smallest thing I have found. I'm not sure if you've read what's written at the bottom of the slide, but basically I was profiling Firefox doing exactly nothing. And it was not exactly nothing, actually, because when I looked at the profile, there were those small spikes. What are those spikes? And actually, it turns out they were the cursor blinking in the address bar. And if I select one of those spikes, like I did here, I can say that making the cursor appear in the address bar uses 1.5 microwatt hours. I was surprised. I didn't expect this to be that precise, but yes, it is that precise. Now is a good time for a live demo, if it works. I assume many of you, when you came here, you wanted to see a map of the campus, especially if you came for the first time. And because you're into open source, you probably use OpenStreetMap. So I will try to figure out how much power it uses to search for the campus on OpenStreetMap. So I will configure a profiler to use the power preset here. Start recording. Open a new tab and type openstreetmap.org. It loads. I have a text field in the top right corner with a cursor in it, so I will type ULB and see what happens. So I'm on a university campus. This is very nice. I don't really recognize the shape of the building, though, so I will zoom out to see if it's in the right place. Zoom out again. Oh, we're in Düsseldorf. Probably not correct. So I will additionally type Brussels. Now that looks better. If I zoom into it, this is actually the building we are in. Okay, I will stop the demo for now, and now we will look at the profile I'm capturing. Again, we have multiple tracks here. Google.com, I don't know why it's here, but I don't care about it. It was probably in the background. I don't care about this either. So I have OpenStreetMap here, and I have the parent process here. I also don't care about how much memory we used. Okay, so this filters down to what's useful. So I have a screenshot track here that orients me pretty quickly. So I was typing the address of OpenStreetMap. Here we had the home page that loaded. And here I had my first results. Here it was animating when I was zooming out to try to figure out where I was. Okay, so let's look at power use now. So the part we might care about is when we actually loaded the right campus, so that's here. So you see the network request here, and you see there's a spike here in power use, and similar here. So I will zoom into this time of a profile. And now this is what happened in the Firefox parent process. So we can see it used about 100 microwatt hours, and in the content process, about 33. So this is about 130 microwatt hours to load the search results showing the campus here. But because we have a profile that's nice, whenever you have a profile, very often you explore other things, because they might be interesting. I'm most interested by the shape that I see here. That seems pretty interesting in terms of power. So I will zoom into it. And we see there was significant power use here. When looking at the screenshot, there were animations going on. So it makes sense that the process doing the rendering uses power. And here we used more than 300 watt hours in the parent process, plus 150 here. So actually, zooming out to see where I was actually used a lot more power than searching for something. We can also see the bandwidth used. So this is the network request, and we see how much bandwidth was used, network bandwidth. So we can see here that zooming out took about 4 megabytes. of network bandwidth. I will zoom out again. I see there's some activity here, and I'm curious about it. I see there are markers. So I will zoom into it and try to see what's going on. There are regular spikes here. I will select the content process here because the markers on the content process, it's likely where the activity started. I will zoom a bit more on one of the spikes. And I said runnable markers, they are very interesting for browser developers because they let us know what's going on. I think I will try to zoom into it to make it more readable. So the marker here, NS caret blink callback timer. So this is actually the timer that's used to blink the cursor that I had in the search field where I was typing ULB browsers. So we can look at how much power it's used. And this is 0.17 microwatt hour in the content process plus 0.8 here. So a little bit less than 1 microwatt hour was used when making that cursor appear. So what I was showing in the previous slide, we can actually do it, and it really works reliably. And I think that will be it for the live demo. I will switch back to the slides. So I talked about many things already, so let's recap a little bit. We have power profiling that works on all the three major desktop platforms, Windows, Linux, and Mac. It's reliable, it's easy to use, you don't need to be root to use it, you don't need to install anything, you just have everything in Firefox. You might be wondering though, Firefox is not shipping only on those three platforms. There's something called Android, where we ship Firefox and have lots of users there too. So what about it? So far, we've not found good APIs that we could use for power profiling, but we had another idea, and this is what I will explain now when talking about external power profiling. If I'm taking a step back from what I was showing before, my first step was to look at how much power was used on the power socket. And this gives us the full picture of how much power is used by the entire computer. But there's one problem. The maximum sampling rate is 50 Hertz, which is in Europe the rate at which the current is oscillating for AC power. And I can't get any much faster data than that. We also got data at the extreme other hand, getting data from the CPU. Very precise data, but missing some of the computer. And it's even worse on a phone because we miss the entire screen or things like this. So the question was, is there anything in the middle we could look into? And yes, there is. If we are talking about mobile phones, or also laptops, there's the charger. Maybe we could instrument the charger instead. And yes, we can. It turns out there are devices that are already on the market that are sold, and their purpose is to test chargers to verify how good the charger is. Check if the current and voltage of the charger is stable. And to be able to do that, they need to sample very quickly. That's very interesting for us. And those devices are affordable, at least if you compare them to the smartphone you use to test your web application on. Some can export data to a computer through USB or through Bluetooth. And one thing that's really important to note to understand how this works is when you charge your battery, when you unplug your charger, you want the battery to be completely full. So anything that was done by the smartphone while your battery was already full, it's still using power from the charger, because if it was taking from the battery would not be full when you unplug the charger. That means that if we wait enough for the battery to be completely full, and we still measure how much power goes through the charger, we actually measure how much power is used by the phone. And that's exactly what we want if we want to power profile. Another interesting detail is some of those power meters, they support more than 200 watts, which is more than enough to power profile any laptop that charges through USB power delivery. So here it's a MacBook that I was charging. So looking at power data from those kind of power meters is what we call external power profiling, and we shipped it in Firefox 121. So how did we make this work? Those devices that are charger testers, there are a few that are available. There's only Windows software that comes with it. The software is in English, which means that every here and there there's Chinese characters. Not sure what they mean. There's poorly documented API. It was nice when I wrote this. What actually that meant is I found one device someday that has what they call an open API. Open API means there's one page of example C++ source code with Chinese comments. That was enough to get started. And then thankfully, they are great and powerful reverse engineering tools. And I tested with this USB light that you can see on the slide here, that has various levels of brightness. And this was a stable load that could let me know which data to expect. And all the power meters on this slide are compatible with the Firefox profiler. And they all produce nice power tracks. Well, some not so nice. Some produce very nice power tracks. And it's plug and play. If you run the script that's in this GitHub repository, and you just plug the device and start power profiling, you will see this power track appear out of magic. And it's nice that it just works because all the Windows software that came with those, it's terrible, you don't want to try to use it. The README file in this GitHub repository includes a list of supported devices, so that's basically the names of the device you saw in the previous pictures. And next to the name of each device, there's a link to an example profile of what you can get from it. What you get from it using, so that was with this USB test light that I was using, various levels of brightness. And you can see in the good example profile that there's what looks like a lot of noise here. It's actually not noise. If you zoom into the profile, you will see that it's a very regular pattern. And it exposes internal details of how the light is using power. It's sampling every millisecond. And if you look at the bad example here, it looks like there's no noise, but it's just because it's sampling every 10 milliseconds, so it's taking an average. And the worst part about it is what's happening here. We are turning off the light, it should use 0 power, but here we see a linear decline for 500 milliseconds. If I want to power profile anything I'm doing with my software, a latency of 500 milliseconds is completely useless, so this device can almost go in the trash. And in all the future examples I will be sharing, whenever you see something labeled USB power, it means power data coming from those kind of external power meters. Here's the first example of power profiling using this system. It's what we call an Android remote profile. Remote profiling means that the profiler was not running on the same device than what was used to start the profiler. So in this case, the profiler was running on an Android phone, running Firefox. And I was controlling the profiler from my laptop that was also controlling the power meter. And when capturing the profile, both sources of data were merged, and we got this profile. We can again validate that it makes sense. You see the shape of the CPU use of the Android device. You see the shape of the power track. They match pretty well, which shows that we're actually measuring the right thing. And the baseline is relatively high here. It's probably because the screen was on at the time. And it's again a profile of loading the Wikipedia homepage. We can see on the screenshots here. So as I said before, there's a link to all my profiles at the bottom of the slides. You can look at them now if you have a laptop in front of you. You can also look at them later if you look at the slides and want to see it again. I have more examples coming next, so I'm giving the links to the slides again. I will mostly be telling you 2 stories on how we use power profiling to understand what was happening. So first story is, I had one of my colleagues telling me, hey Florian, have you seen this new green leaf icon you see in the Windows Task Manager next to Edge? What is it? Can we have it too? So we were wondering what it is. Is it greenwashing? Is Microsoft doing something fantastic about the environment that we should know about? It turns out there's a Windows 11 API to let Windows know that a process is doing nothing that's immediately visible to users, and that instead of optimizing for finishing as quickly as possible, the kernel should optimize scheduling for resource use. We could use this API for Firefox too. And the power profile you see on screen here is the result when using a test case. And the first half of the profile, the test case was in the foreground tab. And the test case is a stupid piece of JavaScript using as much CPU time as it can with an infinite loop. Second half of the profile, the tab was in the background. And we can see the dramatic difference in power use. So yes, this actually does something. It's pretty significant. So putting background content processes in the eco quality of service on Windows 11 is something we shipped in Firefox 108, so that's quite a while ago. We are the first browser to do it, if we exclude Edge that did it when the API was introduced in Windows, of course. Chrome has followed a couple months later, so now I think everybody on the web benefits more or less. And this is great because it actually saves a lot of power. And I will explore a bit more how this works in the next few slides. So we try to do the same thing on Mac. So this is a profile on a Mac with an Intel CPU, and we see the same nice decline in power use. And you will see here that I have power reported by the CPU itself, but also power from the USB power meter. So I checked also the power used by the entire laptop. So they all decline at the same point when we switch to the background. And you can see the numbers, they are pretty dramatic. The cores drop from 18 to 1.6 watts, and the entire MacBook from 30 to 10 watts. The numbers are even better on Apple Silicon, but this example is an Intel CPU to be able to compare with what I was showing for Windows. And next, I wondered, so using less power when doing something stupid like an infinite loop is great, but that's usually not what you want to do with your code in your web pages. So what if the test case was doing an actual computation? So this is computing Fibonacci something, and you can see that when it's in the background, it uses dramatically less power to do the same thing, but also it takes a lot longer. So I have the numbers in the table here. It took more than 3 times as long. It used less CPU, the CPU used less energy, but the entire computer used more during that time. So if you can control the entire system, typically in server environments where once you are done with the task you are doing, you can shut down the server, try to finish as quickly as possible. If you are like us in the situation of a web browser where there are things in the background that have no user impact, but you don't control what happens to the computer because it's the user's computer, then reducing the resource use for everything that's in the background makes a lot of sense. And the way that this works on the CPUs that are not hybrid CPUs, all the cores are the same, is probably by reducing the CPU frequency. And I had one slide where I'm trying to check this, because the profiler can also record CPU frequency. This profile was on Android. And you also see that whenever I have a spike in the CPU frequency, I have a small spike in power use. And when the CPU frequency remained high for a while, the power use was also high. So that kind of confirms the hypothesis here. Second story, this is a real life story. I was trying to fill in a survey that had many checkboxes, and I moved that web page to my external 4K display and put it in a maximized window so that I could see all the things that I was being asked to fill in. And I got distracted, maybe by a baby or something. And came back a few minutes later, and my laptop was super hot, the fan was extremely noisy, and I was wondering what's going on. Of course I profiled. You could have guessed that. And in the profile, I noticed something like this. So this is an artificial test case. I'm not saying what the bad web page was. I could see that the color of the background was slowly changing with a gradient. With my eyes only, I could never see that. Like it was changing over the time of a few minutes. So completely useless animation. And I tried to replicate this with an animation that moves slightly faster so that we see it well. You can see very high CPU core use, high memory power use, high GPU power use, high everything power use. It's terrible. So if you think about it, I said an external 4K display, that means 8 million pixels. I'm on a modern MacBook that has a refresh rate of 120 Hertz. That means we forced the laptop to compute the colors of 1 billion pixels per second. So no surprise that it was hot. And then I tried to explore my hypothesis, because I'm saying it's because there are many pixels many times per second, maybe we could check that it's correct. So on the next slide is the same test case, but I tried to reduce to the minimum the size of the window. And we can see on the shape of the chart the impact that this had on power use. So on GPU power use, the impact was very dramatic. When the window was tiny, there was almost no power use left. You can see there are big spikes here while I was resizing. This is because whenever we change the size of a window, even by 1 pixel, we need to recompute the layout of the browser UI. So high CPU use while resizing, but very low otherwise once the window was small. I have all the numbers on the slide. I won't read them out loud, but you can look at the slides later. Another thing I did to test is there's a hidden preference in Firefox to limit the refresh rate. And I tried various refresh rates. And we can also see that the power use declines dramatically when reducing how many frames we display per second. So this validates the hypothesis we had that it's just too many pixels too many times. So one thing to take away, if you're a web developer and you're thinking about animating the background of a web page, think about it more than twice. It's absolutely terrible. You should not do it. And then I was thinking, okay, many pixels on screen. There's one case where we typically do it is if we are watching a video. And then it makes sense, right? So this is a profile of watching a YouTube video, first in a frame, and then full screen. So you can see in a frame here the amount of GPU power use, and then full screen here. And there are spikes while we were entering and leaving full screen because there's a big animation and things we need to do with the UI. So we can also see that the CPU power use was relatively low. I think this validates that graphic accelerations and hardware decoding were working really well in this use case. So this is all good news. One last example about things to avoid as a web developer. Timers. Waking up a CPU is expensive, especially if you wake it up to do nothing. Using the web APIs, set timeout, you can wake up the thread up to every 4 milliseconds. And this is what we see in this profile. This is a test case that just wakes up the CPU for the sake of doing nothing and sleeping again and waking it up again. And you can see a spike in power use whenever the CPU wakes up. And then the tab is put in the background. And when a tab is in the background, Firefox limits timers to once per second. And you can see this one tiny spike here in power use at the very end. So this shows that throttling timers is a good idea. And this is just about the CPU wake-ups. If you are doing something using actual CPU time in those wake-ups, this would dominate the power profile, of course. And if I have a few more minutes, I have a few more things that are worth sharing. One is Firefox has a built-in process manager. And if you see this icon here, whenever you hover the name of a content process, which is typically what you will care about if you do a website, a profiler icon will appear. If you click it, 5 seconds later, you get a profile of the entire process. And if you are on an Apple Silicon machine where we have per process power data, you will see a power track showing how much power your website used at any given time. You might have seen in my slides and in my demo that whenever I was showing energy values, next to it there was a CO2 equivalent values, which is the equivalent of carbon emissions we would do. Those were created using the CO2GS library from the Green Web Foundation. This was a very welcome contribution we had, so thanks for that. I give a very quick look at the bandwidth track while we were looking at the demo on OpenStreetMap. So a bandwidth track that you have that lets us know how much data has been transferred and converts to CO2 equivalents. This is a suggestion that I got after doing a previous talk in a different place a couple months ago. One of the participants that told me, hey, Florian, power profiling is fantastic. We wished we had a tool like this for a very long time, and it's great for optimizing for performance and sustainability. But you know, what everybody else is looking at is how much data has been transferred, because that's what everybody else was measuring until you had power profiling. And in the Firefox profiler, you already have all the information about networking, because there's all the network requests that are shown. Could you just show how much data has been transferred and put a CO2 equivalent somewhere? Thought about it. Sounded like a great idea, so we did. We did it. And this is shipping in Firefox 1.23, which is currently in beta, shipping in a couple of weeks to release users. Maybe the last thing is if you're out of luck and you can't power profile, and there could be a few reasons. Maybe you're on a virtual machine, so you don't have direct access to the CPU hardware. Maybe you are using a snap package, and then there's nothing you can do. Or maybe you're on Linux and you're not root, so you can't do the magic command to let the kernel know that it's fine to let us know about how much power is used. There's a hidden feature in the profiler because it's not fully polished yet. If you open the DevTools console and type experimental.enable process CPU tracks, you will see new track appearing that say process CPU. And you can see in this example that the shape of the power track and the shape of the CPU's track match extremely well. The one case where they won't match is if you do massive animations, like the full screen animation I was showing before. But I said you should not do that anyway. So if you are not doing anything completely stupid that's feasible, that's something you could look into as an alternative. And as a conclusion, power profiling is possible. It's easy, it's fun. I encourage you to do it. Play with it. It's really simple. This is why I did a live demo, so that you see how simple it is to use it. But if you are really thinking about web sustainability, where you will have the biggest impact, even though it's less visible, is ensure web compat with all browsers, and especially with all devices that still have supported browsers, so think Firefox ESR. And think about good web performance, because even if something is still compatible, if it's super slow, people will want to replace their hardware, and that's where we really lose in terms of sustainability.
Thank you very much for the talk. We've got still roughly 5 minutes for Q&A, more or less. If we've got questions, you can answer. Do we have questions? Please. please raise your hands so we can come to you with a microphone.
Yeah. So, have you ever thought, like, when someone loads a website in localhost and Firefox can detect that it might use too much power to actually show like a pop-up, hey, your localhost app is using too much power, check out Firefox Profiler and Power Meter. Like, would that be feasible to basically push devs to fix their own apps? Would that be like a good idea?
I have not understood. There's so much echo that I couldn't understand what you were saying.
You didn't understand my question?
Yeah, there was too much echo in the room.
Yeah, so basically the question is, have you ever thought to push the Firefox Profiler towards developers when they're running apps on localhost and they're using too much CPU to have like a message, hey, check out Firefox Profiler, it will show you your app is slow and why it's slow.
Okay, so you're suggesting that we could detect the case of web developers because they're running something on localhost and they're definitely developers, and then we should show warning messages.
Yeah, and push, like promote the profiler to devs directly this way.
That's an interesting idea, and not just for excessive power use, but also when something is dramatically slow, we could let them know, hey, you know we have good performance tools, you should have a look at them. Thanks for the idea.
More questions?
You had a question?
So, does like optimizing for power usage differ a lot from optimizing for like CPU usage? Because I guess, I mean, the less CPU you use, the less power you use, and the less network you use, the less power you use. But are there like other things to consider when you're trying to optimize for power usage than just use less resources?
So if I understood the question is there other things to optimize for to use less power other than CPU use? Is that the question?
Yeah.
So the power use is typically first CPU that really dominates, and it's both CPU time and waking up the CPU. Then there's graphics power use, which is what I was trying to show with the examples. And network power use, but you don't control it as much. If you're fetching data from the network all the time, that will use power because it will wake up the Wi-Fi chip, for example. But in terms of scale, CPU dominates so much that's really where most people should focus their attention. At least when thinking about web pages.
More questions?
Another thing I should have mentioned is I have Firefox Profiler stickers on the table here and Firefox stickers, so you might want to take some.
Shiny. Shiny, shiny. Thank you very much.
Okay, thank you very much.
So, thank you very much. Maybe another applause. Thank you.